about materials. And we will begin recording. Thank you.
Okay, can you see my slide?
Yes, we can see your slides and hear you.
Yeah, thank you. Very nice. Thanks, Vera. And my name is Trinh Ben, and it's my very nice opportunity of introduce you to the material science research program. And I will start my presentation now. And so within our mechanical department, we boast a dynamic group of faculty members who are at the forefront of materials development and characterization, with applications spanning various domains. For example, energy. Hopefully, you can see my mouse. And we actually have a bio applications, renewable energy and energy storage, heat transfer, and metamaterials, and also the new function materials. And we do have a lot of applications and development for the advanced characterizations. And our materials program is designed to offer a student a very unique blend of a high quality education and cutting edge research opportunities. Our distinguished faculty are engaged a wide array of research areas. Here I list a couple, and ranging from polymers, thin films, software, actuators, and to battery materials, laser ultrasonics, flashing sintering, nanomaterials for energy and heat transfer. And our graduate students in particular benefit from the wealth of opportunity in specialized in various aspects of material science and engineers. And in our department, and we are proud to have a dedicated team of 15 accomplished faculty members, and I list their headshot here, and who lead the research project in this field. And these professors are at the leading their respective labs and making substantial impacts in their areas of expertise, from discovery of new function materials and for the phonics and thermal metamaterials, electrochemical materials, and also developed novel research characterizations, analytic approaches. And we also create a lot of disruptive technologies for renewable energy and storage. And let me briefly introduce you a few of our faculty members and their area of focus, and to help you understand what we are doing here. So first is Professor Francois Barthelette, and leads a team that dives into the mechanics of deformation and fracture in biological materials, exploring how this mechanism can be replicated in the new bio-inspired energy materials. Here I show the seashell. And the work actually included not only seashell, and include the bone and the teeth and the fish scale and the fish fins. And next faculty, I want to introduce Professor Carson Brown's research. And he leads a team and working on the organic material synthesis, molecular nanotechnologies to engineer materials for various applications. Here, and they're showing that to the photoconductors and how they actually use the organic materials and to create a hybrid photoconductors. And the next one I want to introduce, one of is advanced manufacturing, another is Professor Long Ji Cui, and he will also introduce the third section. And here's the show the Professor Watling research sit at the intersection of additive manufacturing and novel materials function devices. And his work explored unconventional electronic components. And here actually printed ion sensors for monitoring plant sap and hydroponic fluids. And Professor Long Ji Cui research group concentrated on the development of nanomaterials and nanostructure-based tools to better understand the properties of nanoscale thermal, electronic, and optical device. And here's my research, and I'm doing material development for energy storage. And here's the show is one of example we are working in the lithium battery. We also work a lot into in the next generation energy storage techniques systems. And here's the Professor Yi Fu Ding's work. And his work is centered on fabric process and the properties of polymer-based nanostructures. And here's the shows how they are using the synthesis and making different structure and porosity, pores structure, and with the new functionalities. And here's the list of the area strengths. And our material science research encompasses a range of strengths, and including the electrochemical phenomena in microsystems, includes my research and Professor Sehi Lee's research, and we work on the electrochemical phenomena. And we also have a lab on the chip and microfluid devices. And we also have a couple groups working on the micro nanostructure materials for optical materials, energy storage applications. And we also have a couple of groups and focus on the multifunctional energy harvesting and storage. And we have a lot of collaboration with local national labs, as Barry mentioned. We have 4 national labs around, and with the collaborative efforts, we also have a lot of work on the mechanics of nanoscale materials and nanostructure polymers for smart materials and separation applications. And we also have a lot of electronics and thermal photovoltaic renewable energy conversion. And finally, not least, is scalable and manufacturing for micro nanostructure material systems. And here actually, I show the 2 slides here, and at the end of my presentation, I provide you a list of our faculty members and their respective lab website for your reference. And you can actually find the details of individual of each faculty member, their research and their current research team, and also the publications, the recent years publication and collaboration with the local national lab, and also with domestic national labs and international collaboration. And I have 2 slides showing here, and I have all of the faculty members and also lab website and for your reference. So I think that is my brief introduction of our material related science topics and faculty members. And if you have a question, and we will have a breakout room, and I will see you there. Thank you. Okay, I will transfer to the Nick. I will stop sharing my screen.
All right, thank you very much. Let me get mine shared here.
Yes.
All right. Well, good morning, everybody. My name is Nick Botinas. I work in the mechanical engineering department, but also with the biomedical engineering program. So as Vera said, we are all quite multidisciplinary, and I think that's a major theme of the mechanics of materials section. Sorry, my slides are not as pretty as Chinmei's were, but hopefully they can then highlight sort of where the strengths in this area are, starting with looking at physical mechanisms, right? Understanding how physics at different scales allow us to interact with different materials around us. That includes biological materials, plants, animals, everything in between. So we take natural inspiration for the materials that we design, and also use those principles to help better understand those materials. And then hopefully engineer better materials. The idea here is that we can take all of these fundamental principles that we discover and build them into new useful materials in all kinds of different contexts that I'll show some examples of. So the approach that this area takes is a fusion of testing, modeling, and design. So this spans a lot of physical work, computational work, and then engineering fabrication work. And these all come together in some of the different contexts that I'll show you today. So these are some of the folks who work in this research area. You'll notice most of the folks are listed in multiple areas. So if you are interested in any of these sort of crossovers, you might find them in other sections as well. Beginning with somebody who you've already heard a little bit about their research, the Francois group, the Bartholomew group, looking at 2 different projects than Chunmei presented. The first is looking at engineered granular materials. The idea here is looking at how complex engineered geometry, these rhombic dodecahedrons over here on the left, for example, can create densely packed crystals that show really interesting mechanical behaviors. You can see this strain stress curve here with some really interesting properties to it. And all of the physical experiments that are done, the modeling that is done, and developing new materials through what seem like really simple physical principles. I say as somebody who doesn't do that work. That group also takes a lot of inspiration from biology. So you'll see that they here, for example, are studying fish fins and looking at how they move, how they actuate, and creating a new class of material that lives here on this curve of efficiency and stiffness to hit targets that weren't possible with previous types of materials, right? Shown here at the two extremes. So learning from nature around us and then replicating that in materials for different types of applications. The long group does really fundamental studies of material properties, interesting types of materials that are becoming more and more popular across biological applications, mechanical applications. So they are studying how, for example, adhesion, friction, and contact affect how a material behaves. So you can see here their computational modeling that they do to look at those properties. A lot of their work extends to soft materials. This is a really burgeoning area of research, and I'll show a couple more folks working in this area as well. But what they found is that this study of fracture in soft materials was understudied. We understand it really well for rigid materials, but they looked at what happens as they deform, as they crack, as they fracture, and again, pairing together experiments, computational work to understand these mechanics. And then you can use that to design new types of constructs and structures in, for example, composites, right? Understanding how things deform with pressure and heat and force, and use that to engineer better materials. So you can see they go back and forth between that materials and mechanics world in modeling and testing, and then engineering and designing, and doing this in an iterative process. The Zhao group takes some of these principles of soft materials, flexible materials, elastomeric materials, and uses them for engineering design, building structures that just aren't possible with other conventional types of materials. So you can see here they have flexible self-healing materials. They have wearable materials that act as sensors, so they can do temperature sensing, acoustic sensing, ECG sensing. So building in what are normally rigid structures to flexible materials, and looking at what is the complexity of those devices when you do that, and how can they better engineer materials, bonds, and things to have really useful properties for hopefully eventually products. The Vernere group does more fundamental study of materials, and I think that I didn't include the picture here, but they do interesting biologically inspired work. For example, looking at cell mechanics and ant swarms. They've got a really cool paper on looking at how fire ant rafts move and evolve and change, and trying to look at how these natural behaviors can tell us how to build better materials, how to understand how materials work and change, and then use that in engineered materials as well. The Rosine group studies all things waves. So here's one of those very, very multidisciplinary groups that you'll find, where you can see they're studying waves in biological material like skulls, and then waves in engineered material, these quasi-periodic materials. They have some really interesting projects where they pull together what they call Lego-like materials, where you can physically design in the lab and test with all kinds of different apparatus that they have in their lab group, the behavior with vibrations, with waves, and study both failure modes of these materials and information transformation through materials. Here you can see communication of robots through mechanical waves. They span all kinds of different applications and fundamental study. And then some of us live on the sort of fringes of this area where I am using mechanics of acoustics to look at ultrasound imaging. Here you can see some different ways that we try to seek to control mechanics. We try to understand how the acoustic waves interact with tissue and design imaging methods that work in a complementary way with those physics and acoustics and mechanics. We occasionally collaborate with other groups. You can see we do acoustic system characterization. These are little particles that another group was engineering that use oscillating microbubbles to move around, to drive around potentially in the body. And we were looking at acoustic resonances and how to best drive them. And as that a lot of this has applications in the biomedical space. So that's where we spend a lot of our time. So that's it for my slides. And I'm happy to talk with any of you in this area, as well as biomedical, any other interests in the breakout rooms. So with that, I'll turn it over to Longji.
Thanks, Nick. Thanks, Chenmei. So let me share in full screen. Can you see my slide and hear me clearly?
Yes, it's great.
Okay, yeah, great. So, hello everyone. Welcome to our information session. I will talk to you, give you a research overview on our micro nano scale session. My name is Longji Cui. I'm assistant professor of mechanical engineering, also affiliated with material science and quantum material research center here at CU Boulder. If you have any further questions, you can also feel free to send me emails or also visit my website if you're interested in my research. So here we have a quite large body of faculty working in the micro nano field, because micro nano is inevitably also inherently multidisciplinary. So we'll be working with each other a lot, and we'll also reach out to other departments and other theoretical or characterization support very often. So you can look at the link here, which you can find in our department, the faculty tab, to look at a little bit more details of what everybody do. I would like to point you to some resources here, which is a overview, research overview slide deck, have all our faculty's research or most recent research covered. Here are just a few examples. You can see here you'll get a lot more information than probably you can get here from a more skeleton description of the research. I encourage you to go there, check the slide out, and if you have any specific question about the research itself, you can reach out to the faculty following the emails of theirs. And if you have any question about animation, you definitely should reach out to us, the grad committee, Vera, Megan, for help. So I will give you a big picture overview of this field. It is very multidisciplinary. We have focused on mostly 4 topics, and you'll actually see these are the 4 topics covering also material research. One is the basic research on novel micro nano phenomenon and materials. Here is mostly to understand basic physics and basic chemical phenomena effects at the micro and nano scale, which will be very different from the macroscopic scale. And this is why micro nanoscale material and phenomenon become useful in mechanical engineering context. The second one is synthesis of microscale and nanoscale material. To make it useful, to make devices out of this phenomenon, we need to make material and be able to observe. The third one is to do characterization, including surface characterization, bulk characterization, or functional characterization, structural characterization of these nanomaterials, and to develop high resolution instrumentation and tools to make such characterizations happen. This is actually very important because micro nanomaterial, a lot of them you cannot really see, use naked eyes, and you have to benefit from electron microscope or atomic force microscope, these high-end tools, or transmission microscope, or even X-ray MR to observe the function or the device made of nanoscale materials when they are in action. The fourth one, which is directly related to application, is about fabrication and manufacturing of these micro nanoscale devices. And that is very important related to nanoelectronics, nano optics, or any other nanoscale applications, is because us as mechanical engineer will be able to think of ways or develop or invent ways to manufacture such devices and to think about how to scale it up to make it more useful at scale. But further detail, also you can go to the research overview slides. Here I want to talk one potential strength that our micro nano scale faculties has is we have very strong internal external research synergy. These include collaborating with the department here at CU, including physics, chemistry, chemical engineering, material science, electrical engineering, biomedical engineering. And we also have quite a few faculty collaborate with medical campus here at CU, which is in Denver. Also, we have quite a few research initiatives and centers on campus, including the quantum initiative, as CU is a major quantum hub. When you go to micro nano scale, inevitably you need to learn more about quantum, and quantum engineering is becoming emerging front of the whole engineering discipline, including mechanical, electrical engineering. So if you have a very broad research background or education background, you should think about a micro nano scale seriously and maybe eventually go to quantum. And also we have ANSF supported center like STROBE. Pretty we also have MARSAT Center to work on the intersection of quantum, micro nanoscale physics, and chemistry. We also have a large body of research faculty on campus studying quantum materials, including both theory and experiment. And these materials are different, very different from classical material, and could have unexpected functionality emerge from them. And also, as Vera mentioned, we have, that is one of the particular strengths of CU Boulder is because we have several nearby national laboratory, and there are strong collaboration between CU and them. They include NREL, which is Renewable Energy Study Hub of the country, and probably also around the world. Also NIST, which study the most precise measurement and calibration of the standard for different international unit. Also Sandia, a national lab, which is in Albuquerque, is actually within driving distance. It has very good fabrication facility and open facility for us to use. For me, as an example, I have collaboration with a lot of physics, chemistry, and chemical engineering faculty. I'm myself affiliated with material science, and also I'm affiliated with Quantum Material Center. I have collaboration with National Renewable Energy Laboratory. So all other faculty that I mentioned above have similar research portfolio. So now I get into a little bit more details for different sections of micro nano scale material and research. One is the material synthesis and characterization, and we have several like focused research topics that include the mechanics of nanoscale material and system that is directly related to what Professor Nick and Treme have talked about, related to material and also mechanics. Also, we have several faculty work on nanostructure polymer for smart material and separation, including the membrane study applications, and also nanostructure material synthesis and characterization. So here I have several faculty, but this is not a thorough list. You should definitely look at their website for more details, especially their recent projects and funded projects and research topics. A second one is about nanosystem and nano device. And this is the particular strength of mechanical engineering because we are the one who really make real devices to use for real world applications. So here I have several research topics included, including the scalable manufacturing of microstructured material and system. This is very important because if you want to make microscale devices useful, you need to make many of them with low cost and have high performance. And also atomic layer thin film deposition of MEMS and NAMS device. MEMS and NAMS refer to the micro electromechanical system and nano electromechanical system. We also have faculty working on the lab on the chip and microfluid devices. And those faculty typically have collaboration with our medical faculty and even use their device to really solve the medical problems. Carbon nanotube technology for microsystem, also micro nanostructure material for energy storage, multifunction energy harvesting and storage. You can see this research all related very closely with material study. It's because we need to use the physics and chemistry at the micro scale, and we need material to support this phenomenon. stretchable, flexible electronics, and also electrochemical phenomena in microsystem. These are the study not only about the fundamental study of micro nanoscale, but also think about the very particular applications such as electronics and battery, basically for energy storage. And here we have quite a few faculty are listed here, and you can go into their website to look more details. Bio is an emerging topic in mechanical engineering, but also in nanotechnology and nanoscience. We have a new open department, biomedical engineering, specifically devoted to some part of this, and a lot of their faculty actually have their home in mechanical engineering. So here we have several topics, including microfluidics, which is related to how use the microfluidic devices and techniques to manipulate single cells or tissue to study the biochemical phenomenon and actually use that for biomedical application. Human exposure to nanomaterial from consumer products, environmental amplification of incidental and engineering nanomaterials, and this also has a close relation with our air quality faculties who I think we have this in another session, if I'm right, Vera? Yeah, so
Yes.
you can also check that out. Thank you. And also advanced medical imaging and soft matter study. These are all related because when you study tissue, it's inherently soft matter, and medical imaging, if the resolution is high enough, you'll be able to see very, very small aspect of tissue and even cell groups. So here are the faculties. You can take a look. The last one, not the least, is what I mentioned, the very recent emerging topic and discipline in mechanical engineering related to quantum nanotechnology and their application to thermal, transport, and renewable energy. So here I have several topics listed, including the sensors and detectors based on quantum principle, engineering system based on quantum technology. These are basically using the exotic or something we call quantum weirdness and harvest this weirdness to use for sensors, detectors, and try to make real world engineering systems. And some examples that you have probably heard in the news will be something related to quantum sensing, like atomic clock, like the best GPS, or quantum computing, and also quantum information science for communication. Materials based on quantum theory and simulation. This is obvious because when you have a phenomenon, you need material to support it. Thermoelectric, thermophotovoltaic, renewable energy. This is also closely related to my research, which is using thermal energy for renewable energy conversion, because you have a lot of thermal energy wasted directly from any industry processes. Last one is the optical material that can be micro and nano structured. This has research including like Professor Victor Bright and also some of our faculty who have affiliation in electrical engineering. So they're trying to make optical material at the micro scale and to make them very useful. With this, I'll wrap up. If you have any questions, feel free to ask in the breakout room or reach out to us in the future. Thank you.
All right. Thank you.